Barely Berry Jr. here back. I wanted to actually finish this last problem on this first homework. So I want to go ahead and get that done and round this homework out. Then I could come back tomorrow and start on the next homework and get a bit ahead. So we'll go ahead and do that and look at that. This next problem is going to be the free fall problem that I actually had a problem with. I didn't do so well on this problem, I don't think. Certainly didn't understand it so well. So this is the one that says obtain the equation of motion number 23. Obtain the equation of motion for a particle falling vertically under the influence of gravity when friction force is obtainable from a dissipation function. So let me just call it what Professor called it. F equals the dissipation function in the textbook 1/2 k v squared. All right. So I would like say friction forces in the air. Integrate the equation to obtain the velocity as a function of time and show that the maximum possible velocity for a fall from rest is v equals mg over k. All right. So this is the friction force. I would say like air is falling under G. It's going down. So you have a particle that's falling, Fg, and this time we need to use the version of the formula that includes dissipation forces. So the dissipation force formula, let's find it. The dissipation function, here we go. Right here. So the Lagrangian, the Euler-Lagrange equation, I'll just call it ELD, Euler-Lagrange with dissipation, is d dt, partial Lagrangian like we're used to, partial generalized coordinate dot I minus partial Lagrangian over partial generalized coordinate I plus the dissipation force over partial q dot. So the dissipation force is with dot that equals 0. So in order to solve this equation with dissipation forces like friction forces, air resistance, we need to have one term, the dotted derivative of the generalized coordinates of the force of dissipation. Let's go back to the problem. Dissipation function, the function of dissipation. So it's not the dissipation force, the dissipation function. So the dissipation function is F equals 1/2 kV squared. All right. So it's falling. So we have potential energy is 1/2 mv squared, which is 1/2 m. And if I call this v, let me see if she called it plus or minus v. Looks like she called it plus v. So we shall go with that. 1/2 mx dot squared. Potential equals mgh, which equals mgv. So we'll call this potential is 0. and it's falling downward in a positive direction, so potential is positive. So we have the Lagrangian is T minus V, which equals 1/2. Oh, hold up. I left off the dissipation force. Let's put that in the proper coordinates. So D is, no, hold up, we didn't get there yet. So Lagrangian is T minus V, which equals 1/2 mx dot squared minus mgz. Let's see if I have that correct. That's correct. And I'm so used to writing text. And so then we have all I have to do is to order Lagrange for dissipation. Right. It's easy enough to do. So again, I'll do this in parts. I'll do this in 4 parts. 1, 2, 3, 4. All right. So we have partial L over partial Q dot. And actually we have Z dot. We only have one coordinate. So that equals MV dot. Easy enough. D dt of partial L over partial Z dot equals MZ double dot. So this is 1, 2, 4, 3 partial L over partial Z equals negative mg. And for 4, partial F over partial Q dot equals, okay, so you need to rewrite this, 1/2 K V dot squared. Looks like it equals 0. Oh no, it's the derivative of dot. Sorry. So that equals KV dot. Yep, looks right. So now the full order of Lagrange with dissipation forces is going to be full derivative partial L over partial Z dot minus partial L over partial Z plus partial F over partial Z dot equals MZ double dot minus MZ minus MG plus KV dot. And is that a negative in the front? No, it's not a negative. Let's see if this is right. MZ double dot minus MG plus KZ dot. Okay. So now they want to, and welcome who joined. Let me know if you have any questions or comments. I am monitoring the live chat. And right now I'm doing question 1.23, getting the equation of motion for the particle falling under with a dissipation force, for instance, air resistance. So the next thing we need to do, because they want, if we look at the problem, they want show that the maximum possible velocity for a fall from rest is v equals such and such. So the answer needs to be in v. So I'm going to put it in terms of v. So this is mv dot minus mg plus kv v equals 0. So because the answer wants it in terms of v, put it in terms of v. Now, interesting thing here is she differentiates this dt. So this is going to be mv double dot minus 0 plus kv dot equals 0. So this is ma dot plus kv dot equals 0. So this is ma dot equals negative kv dot. Oh, we put everything in terms of a. Makes sense. So we have a dot divided by a equals negative k divided by m. So now the a's are on one side. We have dA over dt 1 over a equals negative k over m. So now we have dA 1 over a equals negative k over m dt. I can integrate both of these sides to get acceleration. Actually, it'll be ln a equals negative k over mt plus a naught, since I integrated by a. Normally I would write a naught, but she's doing something different. Let's just work it out and let's see what happens. Plus a naught. So if I exponentiated each of these, I would have a t equals e negative k over mc and e a naught. So at a t equals 0 equals e a naught, and I'll just call this a naught prime. So the acceleration equals equals a naught prime e negative k over m t. We have an acceleration formula. It wants us to integrate, so we can integrate this. We can have dv over dt. It's interesting how we went past dv. Oh, no, we have v dot. I wonder if we have just come from here, but then we would have had the mg term. So I guess the reason why we took the derivative was to get rid of the mg term. It's kind of interesting. I would think it would lose some data, but it must be okay. So you can take a derivative to get rid of the constant term and then solve for everything else. I think in the past I would have solved for z double dot right there, maybe had a whole bunch of complicated terms. Take a look real fast and see how much different it'll look. So if I had mz double dot equals mg minus kz dot, so this would be m dv over dt equals mg minus k dz over dt. Maybe I'll just leave this as v. So we have m over, see, it becomes very complicated. M dv equals mg minus kv dt. And I have a v on one side, so I can't do that. Yeah, it makes it very complicated. So taking the derivative to get rid of the constant seems to be very good. Right, so I have to keep that in mind. You have a equation of motion, technically. Um, you have a constant that could be throwing things off. Put it in terms of v dot, take the derivative of everything, v double dot, make that into a dot, d over dt, take the integral, and then you have a in a form that's manageable. That's neat. So I guess the constant, the mg at the front, would have just been something that we can level set based upon our choices of coordinates. So now we have dv equals a naught prime e negative k over m t dt. And I'll integrate both sides of this. So we have vt equals a naught prime e negative k. Oh, hold up. Over mt divide by the derivative of that. So that's negative m over k plus v naught. I believe what this will be. Yeah, this is good. Maybe we can do the same thing. V at t equals 0 equals a naught prime negative m over k plus v naught. I'll call this v naught prime. So v naught equals v naught prime minus plus a naught prime m over k. Right? That seems right. So v of t equals a naught prime e negative k over m t negative m over k plus v naught prime plus m a naught prime over k. So this equals v naught prime plus m a naught prime over k, 1 minus e negative a over m t. All right, so we seem to have the same thing here. We integrate it. Let's look at the problem again. Integrate to obtain the equation to obtain the velocity as a function of time. We did that. So we obtained the equation of motion, which would be here, a of t, equation of motion, after the derivative, then integral, derivative to get rid of the pesky constant. Then we integrate it to obtain the velocity. So we integrated a of t, turning it to dv of dt, integrated, found the constant of integration. Now we have v of t, and show that the maximum possible velocity is that, terminal velocity. So as t approaches infinity, we have v of infinity equals v naught prime plus m a naught prime over k, 1 minus 0, because that'll, when you have the infinity in the denominator, it'll make it 0. So we have that equals v naught prime plus m a naught prime over k. I believe that's what she has. I want this in terms of v naught and a. That's because we don't know those constants. We're going to use the original equation. The original Lagrange. Actually, didn't already make this v. Yes, I did right here. So we go into the original Euler Lagrange, ELD, to remove unknown constants. So v dot v dot. We're going to plug this in for v dot. And v dot minus mg plus k v, and it is the entire v of t. This equals m a naught prime e negative k over m p minus mg plus k v naught prime plus m v naught prime over k's cancel, plus m a naught prime minus m a naught prime e negative k over mt equals 0. So m a naught prime exponential, those go away. So we have negative mg plus k v naught prime plus m a naught prime equals 0. Looks like she's solving for a naught prime. Did I never find a naught prime? Yeah, interesting. So you can use the original early Lagrange dissipation equation in the end to solve for a naught prime. So a naught prime equals mg minus k v naught prime over m equals g minus k v naught prime over m. So the v of t, so v of t equals this. Now we have this plug in for v naught prime plus mg minus k v naught prime over m all over k 1 minus e negative k over m t. So this equals v naught prime plus mv over k minus v naught prime s e negative k over m t. So this equals v naught prime plus mg over k minus mg over k e negative k over m t minus v naught prime plus v naught prime e negative k over m t equals, so this cancels, and we're left with v naught prime e negative k over m t. We have that plus mg over k 1 minus e negative k over m t. That seems to be right. So as t goes to infinity, v of t goes to, so this infinity in the denominator makes that go to 0. This infinity in the denominator makes that go to 0. All that's left is mg over k, which is what the solution wanted us to prove we end up with as time goes to infinity. So lots of math trickery in this one. I'll try to keep it in mind. All right. So good night of physics. Hopefully you all enjoy. Thanks for the new subscribes. Help me get to 1,000 subscribers. I'll be back tomorrow to do some more difficult Lagrange problems, so be prepared for that. Hopefully you all enjoy. Hopefully it helps you with your classes or understanding. And I shall see you tomorrow.